gases in the mole, first review sheet. I'm going to work out the even problems here. Again, the odd answer should be online. Let's look at question number 2 here. It asks, at what temperature will 85 grams of ammonia have a volume of 600 milliliters at a pressure of 1200 torr? So again, identify the type of question, because what I will do, or I propose to do, is actually mix up all the different types of questions. So you have to recognize what type of question you actually have. So in this case, it's asking for the temperature, it's giving us a gram amount for ammonia, it's also giving us a volume, and it's giving us a pressure. So yes, we will be using PV equals nRT for this problem, but that's all we're going to be using. Now, you could do a couple things here to solve for this. You could convert the grams of ammonia to moles of ammonia and place it right in there, or you could simply just find the molar mass for the ammonia and then insert it into the PV equals nRT equation by substituting little m over big M for the number of moles. I actually like that, so I'm going to show that way. But again, if you want to do a little bit of converting the 85 grams of ammonia into moles of ammonia, that too is also acceptable. So there's more than one way to work this out. So let me go ahead and show you the PV equals nRT, and then we can substitute for N, which is little m over big M, and it seems like a lot of students enjoy that, so I'll keep doing that. And so the equation now looks like this, where we have PV equals little m over big M RT, and the question here is asking for what temperature. So in this case, we're looking for the temperature, which will be in kelvins. In this case, this actually is your mass. We will find our molar mass for that here in a second. Here's our volume. Make sure you convert that into liters. And hopefully you're getting to the point now where you're saying, okay, I know there's 1,000 milliliters in a liter, so I can simply look at that and say that that is 0.6 liters. If you don't know how to do that, go through the conversion and actually convert it. In other words, for every 1 liter, there's 1,000 milliliters. So start with that and then divide. We will have to convert the torr into either kilopascals or atmospheres. Doesn't matter which way you go on that, so we'll leave that up to the, we'll figure it out here in a second. So let's go ahead and rearrange the variables first before we do any of this. So in this case, we're looking for the temperature. So I'm going to move my molar mass up, and I will divide by, actually let's rearrange and show where we're at this point. So by doing that, we have MPV is equal to little m RT. That might be a little clearer. And since we need to solve for T, we'll divide by M and R on both sides. So now the equation looks like this, where I have MPV divided by a little m R is equal to the temperature. Now, I do need to find the molar mass for my ammonia if I plan on using big M. If you don't plan on using big M, then you'll need to find the number of moles by taking 85 grams divided by the molar mass of the ammonia. Tomato, tomato, it's both the same thing. So ammonia, NH3, has 14.01 plus 3 times 1.008 grams. Sorry for cramming that in there. So real quickly I can get a value, which is equal to 17.034 grams per mole. And we don't want to round that. That's a value that we'll definitely keep in our calculator. All right, so now also we need to convert the torr of pressure, so let's do that. So 1200 torr, and I'm just going to convert that to kilopascals. That seems to be the easiest route here. So 1 kilopascal pressure is equal to 7.501 torr, and I'll give you that conversion. So let's get a value for that. Is 160 kilopascals. My calculator says 159.9786695. So leave that in your calculator as well. All right, so now we have our pressure, we have our big M, we also have our volume, which is 0.6. We have our mass, which is 85 grams. So now let's go ahead and substitute all that in. to this equation here. So I'm going to move you down here so we can actually work with it. All right, so we said that the molar mass was 17.034, and that's grams. And I'm going to put that moles on the opposite side. So again, keeping only one division line, keeps it clean. But again, grams per mole is a molar mass. The pressure we just converted to 160 kilopascals. The volume we said was 0.6 liters. So 0.6 liters. The mass for this sample is 85 grams. And again, that's not molar mass, that's just mass, so that's all it is, it's just grams. And then the R value that we're going to use, in this case, we'll use the 8 or the kilopascal one, which is 8.315, and that's kPa liter, put the mole Kelvin right there. So now we have that. So let's look at what units can cancel out. So again, we have moles are gone, grams go away, kilopascals go away, liters go away, and we're left with Kelvin, which is your temperature. And just make sure you can type all that in. That is a very frigid temperature. That is 2.31 Kelvin. What volume of nitrogen, so we're looking for the volume here, nitrogen gas is needed to react completely with magnesium to form 75 grams of magnesium nitride at a pressure of 90 kilopascals and a temperature of 20 degrees. So we have a pressure here. We also have a mass amount of magnesium nitride, and we also have a temperature here. But let's change that 20 degrees to Kelvin. So add 273. So we have 293 Kelvin. And it wants to know what is the volume. Now, before we even begin, we have to analyze the question a little more closely because we have nitrogen, we have magnesium nitride, we have magnesium, we have stoichiometry. So you have to use the process of stoichiometry, which is, first of all, write a balanced equation. So what volume of nitrogen gas is needed to react? So that means that nitrogen is on the left side, or the reactant side. So it wants to know what volume, so question mark, volume, of nitrogen gases to react with magnesium. And again, it's N2 because of the gin component there. To form magnesium, to form 75 grams of magnesium nitride. And it's going to form 75 grams of that. So let me move you over here, just out of the way. Let's put you somewhere right there. Okay. All right, so let's make sure that we balance the charges. So magnesium's a +2, nitrogen's a -3. So what that means is I need 3 of those and 2 of those. I already had 2 nitrogen here, so I need a 3 here. Actually, let's change that color. Let's get some. So 3 there and a 2 there, which means I need a 3 there. Okay. All right, so our equation's balanced. Let's get rid of that. And let's see here. So we're looking for the volume. We have our temperature. We have a pressure. So what we also have, let's write that down. So let's see. Oh, sorry, over here. So let's move this over somewhere. Actually, let's scoot this all down. Sorry about that. Now that's a little better. So we know our volume, but we also have a pressure of 90. Oops, let's go red. Pressure is equal to 90 kilopascals, and a temperature that's equal to 293. Okay, so we also had that information in addition to the 75 grams. So step 1, write a balanced equation. We did that. Step 2, we're going to take what's given and convert it into moles. So we'll 75 grams of magnesium nitride and convert that into moles of magnesium nitride. So 1 mole of magnesium magnesium nitride on top. And magnesium has a mass of 24.3 grams for every mole. And nitrogen, we have two of those, is 14.01 grams for every mole. Okay. So if we stopped right there, we'd have step 2 finished. But step 3, we need to change the moles of magnesium nitride into moles of nitrogen. So let's put our moles of magnesium nitride down here, because we need to get rid of that. And we're looking for moles of nitrogen. All right, so from the balanced equation, we have 1. Oh man, 101. Daggone it. That kind of stinks. That's boring. All right, so let's find out how many moles that is, because once we find out how many moles that is, that'll actually be our N. Okay, so let's actually do that. All right, so that's around 0.74, 3 moles. All right, so now we have all the fun things here that we can solve. So we're looking for the volume, so let's use PV equals nRT. So PV equals nRT. And I'm looking for the volume, so that means I want to divide pressure on both sides. So now I have volume is equal to nRT over P. And let's go ahead and plug those values in. Let's scoot you on down here. Okay, so my number of moles I just found up there at 0.743. My R is going to be in kilopascals, so let's use that one. So 8.315 kPa liter. Put that mole Kelvin down there. Temperature. What was the temperature again? It was 293. And the pressure is 90 kilopascals. All right, so kilopascals can go away, Kelvin can go away, mole can go away. We're left with liters, which is volume. Awesome. So let's find out what that value is. 20.11, and that's liters. So 20.1 liters is the volume for this gas. If 4 liters of nitrogen reacts with 10 liters of hydrogen at the same temperature and pressure, what is the mass in grams of ammonia produced? So let me ask you, do you think you have a stoichiometry problem? Yeah. Do we have a limiting reactant problem? Yeah. Let's find out why we think that or how that is. So we know it's stoichiometry because we have nitrogen, hydrogen, and ammonia. So let's write that down. So we have 4 liters of nitrogen reacts with 10 liters of hydrogen, and it forms ammonia, NH3. Okay? And the question wants to know what is the mass. So it wants to know what is the mass in grams of that. And we have 4 liters of this, and we also have 10 liters of that. Okay? So here's my question. Initially looking at this, you should not make a judgment on who the limiting reactant is, because we do have a limiting reactant situation because we have amounts for both of the reactants. What we must do before we can make a judgment is balance the equation. So you have to go through the steps first of all. So step 1, write a balanced equation. Is that balanced? It is not. So we need to put a 2 there and a 3 there. Now, once you do that, now it should become apparent as to who the limiting reactant is. However, I still want you to show the limiting reactant step just to support your thought. And hopefully you know what the limiting reactant or who the limiting reactant is. So let's do this. Let's say that I'm going to start with the nitrogen, since that has a smaller value. Doesn't matter which one you start with, we'll still talk our way through it. So I'm going to start with the 4 liters of nitrogen. And the question tells us, or says, that the temperature and the pressure remain the same. So ideally, you would set the conditions at STP, just to speed things along. So if we have 4 liters of nitrogen at STP, and recall that the conditions at STP, if If we're at STP, what that means is that we have our pressure is equal to 1 atmosphere. The temperature is equal to 273 Kelvin. But more importantly, if you have 1 mole of a gas is equal to 1 mole, then our volume is equal to 22.4 liters. Okay, so that's what the really important component of STP is. True, the pressure and the temperature are there, except 1 mole of any gas has a volume of 22.4 liters. So keeping that in mind, we can do some really quick math by plugging in that conversion as long as we're at STP. So 1 mole of nitrogen, okay, and we can find out what that number of moles is, but we don't need to worry about that. What is more important is we want to go through the whole process of the limiting reactant step. So this is our limiting reactant step, which is going to determine which of those two values we're going to use, because we need to find out which of these two amounts is going to run out first, because as soon as the amount runs out, the reaction's done. So we stop right here, we have our moles of nitrogen. Now we can do our mole ratio. So moles of nitrogen here and moles of hydrogen here. So we'll compare the two reactants. We want to compare these two to each other. So in this case, I have 3 moles of hydrogen and 1 mole of nitrogen. All right, now I want to go back to the unit that these are in, or actually what that's in, so I can compare it. If it were in grams, I'd change the moles into grams, but it's in liters. So I'm going to change it into liters. So I'm going to move 1 mole of hydrogen down, and I'll put my 22.4 liters right there. All right, so I can cancel that out, the 22.4s. So essentially what I have is, I have 4 times 3 divided by 1. So what this is saying, in the limiting reactant step, 12 liters of hydrogen. So here's how you should talk yourself through this. If I were to use all 4 liters of nitrogen, I need at least 12 liters of hydrogen gas. Do I have 12 liters? No, I only have 10. So what that means is, I don't have enough hydrogen to completely react with all the nitrogen. So that means that hydrogen is going to run out before I run out of nitrogen. So in this case, my hydrogen is my limiting reactant. Since that's my limiting reactant, that's the value that I want to focus on, not the 4 liters of nitrogen. Let me say it again. If I use all 4 liters of nitrogen, I would need at least 12 liters of hydrogen. I only have 10. So that means that all the hydrogen is going to be used up, and I'm going to have leftover nitrogen, because I don't have enough hydrogen to react with all the nitrogen. So therefore the hydrogen is going to go away, we're going to have leftover nitrogen. Once I know that, then I'm going to take my amount for the hydrogen and do pretty much the same thing that I did up here, except now I'm actually solving for the question. Except the question wants to know, what is the mass in grams? So I'm not going to stop at moles, and I'm not going to use 22.4 at the end, but I will at the beginning here. So 1 mole of hydrogen, 22.4 liters, which is good. I'm still going to do the mole ratio, so moles of hydrogen, and I'm going to compare it to the moles of ammonia. So I want to plug in my values there. So my hydrogen is a 3, my ammonia is a 2. And now, this step is a little bit different than the step above, because I'm changing these moles into grams. So you still don't want to forget that skill of converting moles into grams and vice versa. So keep that in mind. So we have 1 nitrogen, which is 14.01 grams, plus we have 3 hydrogens, 1.008, and we'll find out what that value is there. I get 5. That up a little. So this I get 5.06 grams of ammonia. Pretty cool. All right, the last question. It asks to calculate the density of octane gas in grams per liter at negative 20.3 degrees Celsius. That should be a red flag. At a pressure of 1.55 atmospheres. So let's do this first. Let's change this guy. So negative 20.3 plus 273 is going to be equal to All right, so this equals 252.7 Kelvin. And let's see here. So if we're calculating density, let's rearrange PV equals nRT first. So we have PV equals nRT. We must substitute the value of N for little m over big M. So now the equation looks like this, where we have PV equals little m over big M RT. And since we're looking for density, what that means is that we want to find the units, which is mass over volume. So we need to rearrange all of this so that we have this on one side of the equation. So let's do that. Let's move the volume down here. And I'm actually going to move the molar mass up top just to get some of those variables moving right now. So now the equation looks like this, where I have PM over, actually, is equal to little m RT, and volume's on the bottom. So we've moved the molar mass over, and we've actually switched these two variables. Now, we have our mass and our volume, but we need to divide on both sides by RT. So the equation now looks like this, where we have PM over RT is equal to the mass divided by the volume. So that's how we need to get our equation rearranged before we do any insertion or substitution of any values. So let's go ahead and move this guy over. We can work with that. All right, so let's look at this. So let's substitute the values in. So pressure, do we have a pressure here? We have 1.55. So I'll go 1.55 atmospheres. And my molar mass, I don't think I found the molar mass yet. So let's do that real quickly. So the molar mass for octane, which is C8H18. So C8H18. So that means I have 8 carbons, which is 12.01. Plus I have 18 hydrogens, 1.008. And let's get a number for that. That equals 114. Actually, I'm just going to write it in there. So the molar mass for the octane is 114. 14.224. Don't want to round that too much. So again, that's this. And that's grams per mole. So I'm going to put the mole right down here. So that value is this, the molar mass. The R, make sure that you're using the correct R. I have ATM, so that means I want to use the atmosphere, so 0.0821, and that's atmosphere liter. Put that mole Kelvin on the opposite side. And the last thing is the temperature, which we found to be 252.7 Kelvin. So let's look at our units real quickly. Atmospheres are gone, the moles are gone, and the Kelvin are gone. So we're left with grams over liters, which is density. So let's get a value for that. 8.5. So let's go 8.53, and that's grams per liter.